Underground, in an abandoned gold mine in South Dakota, sits a tank of liquid xenon, cooled to nearly -100 degrees Celsius. A mile of rock shields it from cosmic rays. It's called LZ. It cost hundreds of millions of dollars. Its entire purpose is to detect one single thing: a collision between a dark matter particle and a xenon atom. After years of running, the result is in 0 confirmed detections. This isn't an isolated failure. Across the world, in Italy, in China, in underground labs everywhere, we have spent over $2 billion combined trying to directly detect dark matter. We have found nothing. And yet we are more certain than ever that it exists, making up 27% of everything in the universe. More common than every star, every planet, every atom you've ever seen combined. The story starts in 1933, with an astronomer named Fritz Zwicky studying the Coma galaxy cluster. He measured how fast individual galaxies were orbiting within the cluster. Then he calculated how much mass would be needed to gravitationally hold them together at that speed. The visible mass, stars, gas, dust, was wildly insufficient, by a factor of roughly 400. Zwicky called the missing mass Dunkel Materie, dark matter. The astronomy community largely ignored him for 40 years. Then in the 1970s, astronomer Vera Rubin measured the rotation speeds of stars in spiral galaxies. She expected them to slow down with distance from the center, the same way planets slow down farther from the sun. They didn't. The rotation curve stayed flat, far out beyond where the visible matter ended. Something invisible was providing the extra gravity. Rotation curves are just the beginning. For independent lines of evidence point to the same conclusion. First, gravitational lensing. Massive galaxy clusters bend light from objects behind them. Einstein's general relativity predicts exactly how much bending a given mass should cause. The amount of bending we observe requires far more mass than the visible matter provides. Second, the bullet cluster. Two galaxy clusters that collided. The hot gas visible, X-ray bright, slowed down and separated from the gravitational center of mass, mapped independently through lensing. That means most of the mass passed straight through the collision, untouched. That is not how normal matter behaves in a collision. Third, the cosmic microwave background. The exact pattern of hot and cold spots in the CMB, mapped precisely by the Planck satellite, can only be reproduced in cosmological simulations if dark matter makes up about 27% of the universe's energy content. Fourth, galaxy formation simulations. Without dark matter's gravitational scaffolding, galaxies as we see them today could never have formed in the time available since the Big Bang. For completely independent methods. One answer. Here's what almost never gets explained clearly. We know dark matter isn't just matter we haven't seen yet, like rogue planets or black holes drifting in the dark. Astronomers ruled that out. These hypothetical objects are called MACHOs, massive compact halo objects. Gravitational microlensing surveys searched for them across millions of stars. They found far too few to account for the missing mass. Dark matter also can't be made of ordinary atoms, protons, neutrons, electrons at all. Here's the proof: Big Bang nucleosynthesis. The relative abundance of hydrogen, helium, and lithium produced in the first 3 minutes after the Big Bang depends precisely on the density of ordinary, baryonic matter. The observed abundances match a universe with only about 5% ordinary matter. Confirmed independently by the cosmic microwave background. Dark matter must be a fundamentally new kind of particle. Not in the standard model. Something that interacts through gravity, barely interacts, if at all, through any other force, and has never been created or directly detected in any particle accelerator on Earth. So what is the leading candidate? For decades, the favorite was the WIMP weakly interacting massive particle. The theory predicted WIMPs would have been produced in the early universe in just the right abundance to match dark matter's observed density today. A stunning coincidence, called the WIMP miracle. This made WIMPs the prime target for detectors like LZ, XENONnT, and Panda X4T, all racing to catch a WIMP colliding with the nucleus of a regular atom. The sensitivity of these detectors is almost incomprehensible. The latest results rule out WIMP interaction cross-sections down to about 10 to the minus 47 square centimeters. That means a WIMP could pass through the entire Earth and have only a 1 in a trillion chance of hitting anything at all. We've pushed sensitivity up by 6 orders of magnitude since the 1980s. And still, nothing. This has driven physicists to take other candidates seriously. Axions, ultralight particles tied to a completely separate standard model puzzle. And primordial black holes, formed in the first second after the Big Bang, too small and too old to have evaporated yet, but potentially numerous enough to make up the missing mass. The hunt has widened. The mystery hasn't shrunk. Here are the numbers that should stop you in your tracks. 90 years since Zwicky's discovery. $2 billion and counting, spent on direct detection experiments. 0 confirmed particle detections. Dark matter outweighs all the ordinary matter in the universe, every star, every planet, every human being who has ever lived, by more than 5 to 1. If you could see dark matter, the Milky Way, the bright spiral of stars, would be a small glowing core inside an invisible halo roughly 10 times larger in diameter, and a trillion times the mass of the Sun. We are not failing to find dark matter because we're bad at looking. The LZ detector alone can now rule out a WIMP cross-section so small that, on average, such a particle could pass through a wall of lead stretching from here to the nearest star without hitting a single atom. We are succeeding at ruling out almost everything dark matter could be. Which, paradoxically, makes the mystery deeper. Some physicists now seriously entertain the possibility that dark matter isn't a particle at all, but evidence that gravity itself behaves differently on galactic scales. A theory called MOND, modified Newtonian dynamics. Most of the evidence still favors particle dark matter. But after 90 years, certainty about its existence has not translated into knowledge of its identity. We've mapped dark matter's gravitational footprint across the entire observable universe. In galaxy rotations. In gravitational lensing. In the cosmic microwave background. We know precisely how much of it there is. 27%. Accurate to a fraction of a percent. And after 90 years and billions of dollars, we still don't know what a single particle of it is made of. That's not a failure of physics. That's physics doing exactly what it's supposed to do, refusing to accept we don't know as a final answer. Next episode, we tackled the other 68%. Dark energy. The force accelerating the expansion of the universe. And why it might be an even bigger mystery than dark matter itself. Subscribe. New physics every week. See you next week.